Hello students. In our previous session, we had learned the need for rational numbers. What are these rational numbers? The numbers of the form p by q, where p and q both integers and q not equal to 0 are called as rational numbers. For example, if we have 2 by 3, negative 3 by 4, these are all rational numbers. Not only that, the number 5 is also rational number. The reason being, 5 can be written as 5 upon 1, and in this case we don't have q equal to 0. So all these, they are in the form of p by q, where p and q are integers, and very importantly, q is not equal to 0. Then the question arises, why q shouldn't be equal to 0? We have learned that a number 1 upon 2 is 2 divides 1. When we divide 2 by 1, we get something like 0. It becomes 10. 2 5 times is 10. We are going to get 0.2 as a quotient. At the same time, when we have some number which is divisible by the denominator, say 10 by 2, 2 divides 10 5 times. In this case, the quotient is 5. So each time we divide numerator by a denominator, we are going to get a quotient. What if the number 1 is divided by 0? When 0 divides 1, what will be the quotient? Can you guess a number here? We do not get any number as a quotient. So it means that the quotient doesn't exist. This quotient doesn't exist in two different cases. The case 1 is a number 0 divided by 0, we do not have a quotient, and any number divided by 0, we do not have any quotient. That is the reason why we do not have q equal to 0. I said in the previous session that a positive fractions and negative fractions combined together forms a rational number. So how do the rational numbers differ from fraction? Fractions are like 1 by 2, 3 by 4, 3 by 2. These are all fractions. If you observe carefully, you will come to know that they are all positive numbers. If you have numbers say 5, 6, 10, these are all positive integers. If you have the numbers say negative 1, negative 2, negative 15, these are all the negative integers. The 0 is a whole number and also an integer. I can write 0 as 0 upon 1. These are all. So this particular number is a rational because it is in the form of p by q. Now for instance, if I consider negative 1 upon 2, negative 3 upon 4, negative 3 upon 2, I have considered all these numbers only with negative sign. These are all negative numbers. They are the negative fractions here. These are the fractions. These things are the negative fractions. These are all in the form of p by q, where p and q both are integers and q is not equal to 0. So I mean to say that a rational number is a larger set than fractions because both the positive fractions and the negative fractions are present in the set of rational numbers. Now when I look at the Venn diagram representing rational numbers, we observe that the natural numbers are present in the set of whole numbers, and all whole numbers, including the natural numbers, are present in the set of integers. The integers, whole numbers, and natural numbers in turn are present in the set of rational numbers. Any number that can be written in the ratio as p by q, this includes integers, fractions, and repeating and terminating decimals are called as rational numbers. What does this repeating, terminating decimal refers to? When I consider the number 1 upon 2, it is nothing but 0.5. It's a terminating decimal. For instance, if I consider 1 by 3, it becomes 0.3 recurring. Or it can be written as 0.3 bar. This bar indicates that that particular number repeats. So this is a repeating decimal. This particular thing is a repeating decimal, and this one is non-repeating but terminating decimal. All the rational numbers, when expressed in a decimal form, they either terminates or repeats. So there are two definitions for rational numbers. The definition one is the numbers of the form p by q, where p and q are integers and q not equal to 0. The definition 2 is the numbers, when expressed in decimal form, either they terminate or they repeat. So there are two definitions for a rational number. You must remember both of them. Next, moving on, we need to learn the properties related to the rational numbers. What are these properties? The properties are closure property, commutative property, associative property, distributive property, the existence of additive identity element, multiplicative identity element, the existence of additive inverse, multiplicative inverse in the number system. So we will take up each one of the number systems and we shall discuss in detail each of these properties. First, we will start with closure property. We will take up closure property in the set of natural numbers. As we know, there are 4 operations we shall discuss the closure property of natural numbers under the operation addition. If a and b are any two natural numbers, then a plus b is equal to c, where c is also a natural number, then the set of natural numbers are said to be closed under addition. If a and b are any two natural numbers, let me take two of the elements from the set of natural numbers. We know that the natural numbers are represented as n equal to 1, 2, 3 and so on. Let me consider any of the two natural numbers from the set of natural numbers. Let me take, say, 4 and 5. When I add them up, the sum becomes 9 and the set contains 9 also. 4 and 5, they belongs to the set of natural numbers. Their sum also belongs to the set of natural numbers. So we say that the natural numbers are closed under addition. Now if I consider other two elements, suppose if I take 5 and 3, their difference 5 minus 3 is 2. 2 is present in the set of natural numbers, but then if I consider 3 minus 5, we get negative 2. Here it is present in the set of natural numbers, but negative 2 is not present in the set of natural numbers. So look at the statement here. If a and b are any two natural numbers, then a minus b is equal to c, where c is not a natural number always, then the set of natural numbers are said to be not closed under subtraction. Here, when I consider the difference of the numbers, I am getting negative. This particular negative number is not present in the set of natural numbers. So the set of natural numbers are not closed under subtraction. Now I'll consider another operation, multiplication. Suppose if I consider the multiplication of the number 5 and 3, five into 3 is 15. Clearly, when 5 and 3 are present in the set of natural numbers, their product is also present in the set of natural numbers. If a and b are any two natural numbers, then a into b equal to c, where c is also a natural number, then the set of natural numbers is said to be closed under multiplication. Look at another operation, say division. If I consider divided by, when 5 is divided by 3, we get 5 by 3, which is not present in the set of natural numbers. When I consider 10 divided by 2, no doubt 5 is present in the set of natural numbers, but then we have to see this particular thing always. If a and b are any two natural numbers, then a divided by c A divided by B equal to C, where C is not a natural number always, then the set of natural numbers are said to be not closed under division. Here 5 by 3 is not there in the set of natural numbers, whereas 5 is present in the set of natural numbers. So we have to look into the word always. So look at subtraction and division. The natural numbers are not closed under these two operations, whereas under addition and multiplication they are closed. We shall look into another set of whole numbers. In the set of whole numbers, when I consider the operation addition, they are closed because sum of any two whole numbers is a whole number. When I consider multiplication, they are closed. When I consider subtraction as well as division, they are not closed. The same thing is it applicable in the case of the set integers? Let's look into that. When we look at the set of integers, if a and b are any two integers, then the sum of the integers is also an integer, then the set of integers are said to be closed under addition. Let me consider the set of integers. The set of integers, they contains negative numbers, 0 and positive numbers. Suppose if I consider minus 3 and minus 2, their sum is negative 5. Negative 5 is an integer. If I consider positive 10 added to negative 5, I get positive 5. It is also an integer. So when we take any two integers, either positive or negative, we always get the sum as integer only. So we say that the set of integers are closed under addition. When I look at the operation subtraction, suppose if I take subtraction here, do I get the result as integer? Let's check it out. Here I'll consider negative. It becomes negative 3. Negative of a negative number is positive plus 2. The sum is negative 1. When I consider 10 minus 5, I get positive 15. Clearly, negative 1, positive 15, they both are present in the set of integers. So in the subtraction, also we get that the set of integers are closed. So in addition, subtraction, they are closed. What if I consider multiplication? If I consider multiplication, will the product be an integer? Let me take the operation product. Negative 3 multiplied to negative 2 is positive 6. Clearly it is an integer. Positive 10 multiplied with negative 5, I get negative 50. You consider any two integers, their product is also an integer. So we say that the set of integers are closed under multiplication. What if I consider division? Suppose if 10 is divided by negative 2, we get the result as negative 5. It is an integer. Suppose negative 2 is divided by 10, I get -1 upon 5. It is not an integer. Therefore, the set of integers is not closed under division. With this, I would like you to think about the closure property in the set of rational numbers. Can I say that the set of rationals are closed in either addition, subtraction, multiplication, and division? Just think about it. With this question, I am ending today's session. Thank you.